In this video, we continue our exploration of the fascinating world of complex numbers, where real and imaginary intertwine to unlock new dimensions of mathematics. Today, we're going to delve deeper into the intriguing realm of imaginary numbers, shedding new light on their inner workings and significance in the process of unraveling the mystery. So this video was inspired by an email conversation I was having with a colleague of mine, and we were discussing imaginary numbers and complex numbers and quaternions. And we hit a bit of a roadblock when discussing some of the concepts behind the imaginary number and in the way things are written. And so we hit kind of a bit of a roadblock. And so I decided instead to make a video about this because sometimes I explain things in videos better than I do in one-on-one conversation. It's very easy for people to misunderstand each other when we're having these kinds of conversations. And so I thought this might be a good opportunity for me to make a video and to explain things in the most transparent, least ambiguous way possible. So I'm going to map this out as carefully as I can so that I say exactly what I want to say without being interrupted and without being contradicted. And then hopefully this can resolve the problem that I was having with this particular person. But before we get into any of this, I think it's a good idea that we all brush up on our math a little bit, okay? I think it's a good idea every once in a while to go back and make sure that the foundation for our mathematical understanding is solid. And so this is going to be helpful for people that don't think that they're good at math. And this is also going to be helpful for people to understand what I am saying when I am talking about these concepts, okay? So we're going to start out with something I refer to as the anatomy of a number. So here we have the number 9. Now I'm sure everyone understands what the number 9 is. When you write the number 9, you understand what this is. You make some assumptions about what this is. But when you write the number 9, there's actually a lot of stuff missing, and there's a lot of stuff hidden in mathematics and in algebra. There are a lot of things that we don't write because there are certain assumptions that we make. Okay, so in reality, when we write the number 9, what we're writing is this. Okay, we're writing number 9, the quantity number 9. Okay, I refer to this as a primitive number. Okay, and then we have the positive or negative operator, okay, positive or negative symbol. And then to the right, we have the identity. So we're going to deal with these parts separately, and we're going to start with the easiest part, which is the quantity, which is the number, which I refer to as a primitive number. Okay, these are primitive numbers. And the primitive number, okay, doesn't have the plus sign and doesn't have the identity. It is just the raw number, okay? So the primitive number, okay, the primitive numbers are just quantities, magnitudes, and distances. They could also be weights. So anything that just has a magnitude or a quantity can be referred to as a primitive number. So you can have integer primitive numbers, you can have fraction primitive numbers, you can have fractions written in decimal format, you can have irrational primitive numbers, okay, like pi and tau. Oh, that did that wrong, 1.6.28. And of course, 6.28 is 2 times pi, okay? So again, primitive numbers are magnitudes, they're quantities. So they're quantities, so you can have a quantity of apples, for example. Magnitude could be measuring the height of someone. Distance is also a primitive number. When you measure the distance between someone, you just have 6 feet. Remember the good old days, 6 feet. Stand apart 6 feet so we can't talk to each other. Yeah, I'm not bitter at all. And then we have the weights. You know, you can have a weight, which you would also just use primitive numbers. So there's no such thing as positive and negative quantities, positive and negative heights, positive or negative distances, or positive and negative weights. So that's pretty straightforward. Okay. So in this video, I put curly brackets. I'm going to put curly brackets around the primitive numbers just to distinguish them from other numbers that we're going to talk about. Okay, so basically what I'm doing here is I am separating out the positive and negative operator from the primitive number from the identity of the number. So next we're going to talk about the identity of a number. Okay, so the identity of a number, is a number such that when multiplied by any other number leaves that number unchanged. Okay, so the identity of the real numbers is 1, and because 1 times 10 is equal to 10. Now, for the sake of the discussion in this video, I am putting identities in square brackets, okay? Identities are also sometimes referred to as units. And so, as you may recall, in unit analysis, I am quite rigid, diligent about putting units in square brackets. So I'm going to use the same square brackets here for the units, and this is the unit of the 1 is the unit of the real numbers, and it's also the identity of the real numbers, because when you multiply 1 by any other number, whether it be positive or negative, any other real number, okay, whether it's positive or negative, then you are going to get back that number. Okay, so that is why I put this here. Okay, when you multiply the identity of the real numbers with the numerical value of 9, actually this is positive 9, then you get back positive 9. Okay, so now there's another kind of number, there's another kind of identity. Okay, there's another kind of identity which has to do with the imaginary numbers. Now we'll get into more about this in a few minutes, but I just wanted to put this here for the sake of completeness. So 1 is the identity of the real numbers. Okay, 1 is the identity of the real numbers, and I is the identity of the imaginary numbers. Okay, so this is extremely important in the discussion that we're going to have, because we need to clearly distinguish between real and imaginary numbers, and the way we do that is we assign an identity. So 1 is the identity of the real numbers. So you can imagine that beside every real number, there is a little 1 in square brackets beside that number. Now, because real numbers kind of came first, we generally don't write the identity of the real number every time we write a real number, but this is what we're going to do in this video. I think because we need to distinguish between real and imaginary numbers, and the way we do that is with these identities. You can imagine that these identities identify the number. Okay, so what I'm going to do here is I'm going to do something. Instead of putting a 1 here, I'm going to put an R here. So R is the identity of the real numbers, and R is equal to 1. Okay, so we're going to abstract the identity a little bit. This is going to be helpful when we get into more details. Okay, so I'm going to write R as the identity of the real numbers, knowing that R is equal to 1. Okay, and I is the identity of the imaginary numbers, but we don't know what I is yet. Okay, so we know that R equals 1. We know that 1 times 9 is equal to 9. 1 times positive 9 is equal to 9. And we know that I times positive 9 turns this number into an imaginary number. Okay, putting an R beside this, another way of looking at it. Putting the R beside here turns this number into a real number, and putting an I beside this turns this number into an imaginary number. This is the identity. Okay, it identifies, we're identifying, distinguishing between real and imaginary numbers. We're identifying this number as a real number and this number as an imaginary number. So next we're going to talk about operators. Okay, operators are symbols that we use in mathematics to operate on numbers. Okay, so we're going to start with the multiplication and division. Okay, the multiplication and division operators are pretty straightforward. Everyone knows what they are. The times sign, the x sign is times. 3 times 3 equals 9. 9 divided by 3 equals 3. So these are referred to as operators. And so this is, and the square root symbol is also an operator. And there are other operators. But I just wanted to talk about operators in general, just to get us started on what I really want to talk about, which are the positive and negative numbers. Okay, so positive and negative numbers have these operators. This is the plus operator, and this is the minus operator. Okay, so this with these operators, you can do addition and subtraction, of course. Everyone knows that. But without these operators, it's very difficult to do addition and subtraction. And so here we have addition. So 1 plus 2 equals 3, and 3 minus 2 equals 1. Okay, so this is pretty straightforward. We don't need to go over this anymore. This is definitely kindergarten math, okay? But now we're going to talk about the multiplication rules for the plus and minus operators, okay? So this is actually where the problem arises from the square root of -1, okay? The square root of -1 has nothing to do with the 1 and has everything to do with these operators, these multiplication rules for the operators, okay? So again, this is, that very early grade math, but I think it's important to talk about it because this is the source of the problem for the square root of -1. Okay, so I put these operators in round brackets just to distinguish between these, just to make it look better actually, and so to clearly separate the plus operators from the multiplication operators. Okay, so the multiplication rules for operators are as follows. Plus times plus equals plus. Minus times minus equals plus. Plus times minus equals minus. And minus times plus also equals minus. Okay, so when you have two numbers that have plus signs in front of them, you end up with another number with a plus sign in front of it. And when you multiply two numbers with a minus sign, minus operator in front of it, you end up with a number that has a plus operator in front of it. So now we have everything we need to continue with the original discussion. Okay, so we have the anatomy of a number, we have the quantity of the number, we have the sign of the number, which when positive, we often don't write it. But for the sake of this discussion, I'm going to write the plus sign to clearly distinguish positive numbers from negative numbers. So if there's a negative number, I'm going to write negative, and if there's a positive number, I'm going to write positive. And when we're talking about real numbers, I'm going to put an R beside that number to clearly distinguish it from the imaginary numbers, where I put a little I in front of the number. And we know that the identity of the real number is equal to 1, and this is what we're going to try and solve. Okay, so this is the source of the problem. In terms of the language, now, I always say the problem is with the language. Well, the problem is with the language. So anytime I get into an argument with someone about this, it's 99.999% of the time, it is the language. It is the way people are saying things. It is the way people are communicating these ideas, which may or may not be a little bit misleading. Okay, so I'm going to go back to the original discussion, but I wanted to do this little refresher course. I wanted to make sure that we are all on the same page when we're discussing these ideas. So let's quickly go through. This is just one part of the email exchange, but this was the part that raised most of the problems that we were having with this conversation. Okay, so we had already been having a bit of a conversation about it. So he wrote back to me that I wrote, technically, so in a previous email I wrote, technically the square root of -1 has two solutions. Okay, square root of -1 has two solutions, I and minus I, and he came back with, this is incorrect. First, this is not the square root of 1, but the square root of -1, which is quite different. Okay, so at first I thought he was saying that what I said here, the square root of -1 is I and minus I. But then looking at this more closely, I realized I left out the negative word here. So I said technically the square root of 1 has two solutions, which is true. But then here I corrected myself and wrote the square root of -1. So I was hoping that he would notice that I just misspoke here and that this is really what I was talking about. So I have to give him the benefit of the doubt that when he said this is incorrect, that he was talking about, maybe a bit confused about what I said here. But really I was just misspeaking and I should have put the negative word in there. And so that's kind of my bad. Okay, so this is not square root of 1, so this may have caused some confusion. And this is where, email exchanges, if you don't, proofread things properly, you can really end up in a bad situation, okay? So, but this is not the problem. I was really talking about this, and what I said is technically the square root of -1 is I and minus I, where I is the identity of the imaginary numbers. Okay, and then so then he came back with, second of all, since I is equal to the square root of -1, okay, this is where I have a problem right here, which means that I is the square root of -1. Well, he wrote that here and then wrote it again. I guess he was just being clear. Then minus I is equal to minus the square root of -1, minus I minus square root of -1. So yeah, that is true. I don't have a problem with any of that. But I have a problem with writing this statement right here, I is equal to the square root of -1, because the square root of -1 has two solutions, I and minus I, and so you can't really say I is equal to square root of -1 when I, square root of -1, has two solutions, I and minus I. So I times I is equal to -1, and minus I times minus I is equal to -1. Okay, so this is really what I'm objecting to. Okay, and then, so that's why I wrote, what about the negative solutions? In terms of mathematical rigor, the statement I equals j equals k equals the square root of -1 is not exactly true. And then he said, well, I did not come up with this idea. You would have to discuss this with Hamilton. Okay, so Hamilton is the famous mathematician, which we will talk about eminently because unfortunately Hamilton died now more than 200 years ago, 250 years ago, or however long he has been deceased. And so he's the one, he did not come up with this idea. Okay, he did not ever say, I'm pretty sure he never said I equals j equals k equals the square root of -1. This is not what he is famous for, okay? So this is what we're going to talk about in the next section. So I found this video called Hamilton and Quaternions Are Amazing by this lady here, Kathy Loves Physics and History, and I like her videos because she is a very great historian, I think, and she is very thorough, but also she makes history fun. So when I listen to her talk, it gets me excited about the history of mathematics and all the characters that played into the history of mathematics and electromagnetism and all that stuff. So she is quite good. I highly recommend her videos on these subjects. So at the beginning of this video, she's showing a sculpture of Hamilton here with his beautiful wife, and he had been on a walk and he had a revelation. Okay, he had a revelation that about quaternions, which he's engraved into this wall here. I think it was a bridge. And he wrote I squared equals j squared equals k squared equals ijk equals -1. Okay, and this is beautiful. This is perfect. There's nothing, absolutely nothing wrong with this statement right here. So notice that what Hamilton actually wrote was I squared equals j squared equals k squared equals minus 1. And he did not write I equals j equals k equals the square root of minus 1. Okay, it may seem like a small point, but what I'm going to be able to prove to you is that this is technically not correct, but this is. Okay, so there's a big difference between writing this and writing this. Okay, Hamilton did not write this, he wrote this. Okay, and this is an extremely important point, and so I'm going to get into more details about that. So if we go back to this email, you'll see that I am saying that the square root of -1 has two solutions, I and minus I. And this person is saying that I is equal to the square root of -1. And of course, it can't be both. It can't be both. We can't both be right. Either the square root of -1 has two solutions, I and minus I, where I is the identity of the imaginary numbers, or I, the imaginary identity of the identity of the imaginary numbers, is equal to the square root of -1. But the square root of all numbers has two solutions. So how can I be equal to the square root of -1 when the square root of -1 has two solutions? And so that is the problem I'm having. He is assuming, so he's saying since I is equal to the square root of -1, so he's assuming that I is equal to the square root of -1, then he is obviously assuming that this is true, and I am assuming that this is true. Okay, so what we're going to do is we're going to look at this is the Wikipedia page for the imaginary unit, and this is what we're talking about. Okay, and you're going to see right here that it says, literally says, there are two complex square roots of -1. So the square root of -1 is I and minus I, just as there are two complex square roots of every real number other than 0. Okay, so this is literally saying there are two complex square roots. Now notice they're saying complex square roots. This is actually very important. The square root of -1, so the square root of -1 has two solutions, I and minus I. So when we go down this page a little further, we're going to see this here. So it says the imaginary unit I is defined solely by the property that its square is -1. Okay, so here they're saying I squared equals -1, which is very similar to what Hamilton is saying here, except he's talking about quaternions. And so he's got I squared equals j squared equals k squared equals ijk equals -1. And here we just have the I squared equals -1. So I squared is equal to -1. Okay, so I squared is equal to -1 is true. Okay, this is true. But the problem is when you take the square root of both sides. Okay, the square root of I squared is equal to I, and then you end up the square root of 1. So it looks like you could say that I is equal to the square root of -1, but this is not true, because minus I squared is also equal to -1. And so there is a little bit of a logical problem here, and this is what I want to try and help us sort through. So let's have a look at this a bit more closely. Now it looks like you could say if I squared is equal to -1, then the square root of I squared, which is I, is equal to the square root of -1, and end up with this statement here that I is equal to the square root of -1. Now this is analogous to saying if 3 squared is equal to 9, positive 9, then the square root of 3 squared, which is 3, is equal to the square root of 9, and no one would ever say this, okay? Because we know that the square root of 9 in the real number system has two solutions, plus 3 and minus 3. So positive 3 times positive 3 is equal to 9, and negative 3 times negative 3 is equal to 9. So no one would ever say that 3, if that 3 squared equals to 9, therefore 3 is equal to the square root of 9. So why would we say I squared when I squared equals to minus 1, therefore I is equal to square root of negative 1? So this is why I have a problem with that statement. This statement right here, okay? So this person is trying to say since I is equal to the square root of negative 1, which is technically not true, okay? Hamilton did not say I is equal to the square root of negative 1. Hamilton said I squared is equal to negative 1, okay? So I is not equal to the square root of negative 1. I squared is equal to negative 1. Okay, so hopefully that makes sense. Let's go back to this right here. Okay, this logic is fairly straightforward. So no number squared. Okay, this works with any number, whether it's an imaginary, the identity of the imaginary numbers, whether it's the identity of the real numbers. So no one would say, if you put a 1 here, and so 1 squared is equal to positive 1, therefore 1 is equal to the square root of positive 1. Okay, 1 is not equal to the square root of 1. The square root of 1 is equal to 1 and minus 1. Okay, so no one would ever say 1 squared, since 1 squared is equal to 1, therefore 1 must equal to the square root of 1. No one would ever say that. So why would we say something like this? This is a syntax error. This is a bug in the program. If someone is using this as the basis of their theory, then I am going to have a problem with that theory. Unfortunately, this is a common mistake that people make. It is a common mistake for people to assume that if I squared is equal to minus 1, then the square root of I squared is equal to the square root of minus 1. In fact, if you go to this video and you look at around the 8-minute mark, you'll see that this person actually wrote that in this slide. They did a derivation. They made an incorrect assumption about what Hamilton was doing, and they wrote I is equal to the square root of minus 1. So in this video, she is claiming that Euler said that I is equal to the square root of negative 1, and that Hamilton is claiming that I is equal to the square root of negative 1. But when I look at the page that she showed to show that Euler claimed that I is equal to the square root of negative 1, you see this little formula here. Okay, so this is x plus y times the square root of negative 1. And so this is not equal to I. Okay, this is not equal to I. X is equal to, so x plus y times the square root of negative 1 is equal to x plus y times I, the identity of the imaginary numbers, and x minus y times I, the identity of the imaginary numbers. Okay, so I does not equal to the square root of negative 1. The square root of negative 1 is equal to plus and minus I. Okay, so Euler definitely wasn't saying that I equals the square root of negative 1. He was saying the square root of negative 1 is equal to positive I and negative I. Exactly what I was saying in my email. Okay, so let's go back to that. I was saying that the square root of negative 1 has two roots, I and minus I, and technically that is what Euler is saying. Here, he's saying that x plus y times the square root of negative 1 has two solutions, x plus y times I and x minus y times I. So let's look at this a bit more closely because the text in that page was a bit too small. And so what Euler was writing was this formula right here. So he was writing x plus y times the square root of negative 1 is equal to x plus y times I and x minus y times I. So this function here, this formula here has two solutions. Okay, this quadratic equation has two solutions. Okay, so when I went to high school and when I went to university and I had to write a math test, excuse me, I had to show all my work. Okay, I would lose marks if I didn't show all my work. And so I'm going to show you there's an intermediate step getting from here to here, and that's this step right here. Okay, so this quadratic formula here, x plus y times the square root of negative 1 is equal to x plus y times positive I and x plus y times negative I, where I is the identity of the imaginary numbers. Okay, and so this is the intermediate step that they usually don't write, that Euler didn't write in that paper. And this makes it much more clear that the square root of negative 1 is positive I and negative I, where I is the identity of the imaginary number. And so this here simplifies to this x plus y times I, and this one here simplifies to x minus y times I. Okay, but basically what you need to see, what I want you to see is this right here. So the square root of negative 1 is equal to positive I and a negative I. Okay, and I think that some people get confused because if you don't write this part here, okay, let me just, I'm going to hide that. Okay, I'm going to hide this for now. If you only saw this here, you might get the false impression that this square root of negative I, because this is beside the y, okay, and the I is beside the y and the I is beside the y, that you might think that I is equal to the square root of negative 1. Okay, but when you put the intermediate step in, okay, this goes to here and goes to here. Okay, so when you write everything out in full, it makes it abundantly clear that the square root of negative 1 is equal to positive I and negative I, where I is the identity of the imaginary numbers. Okay, so this is, I think, very important. There's also something, interestingly, there's also something else missing that Euler doesn't write in his paper, and I'm just going to briefly go over that. Okay, so first of all, I'm just going to write the square root of plus 1 beside the x, because the x is the real component of this quadratic equation, and the y is the imaginary component of this quadratic equation or formula. And so this is actually more complete than what Euler wrote in his paper, okay, than what everyone writes, basically. But is just as correct to put the square root of negative or of positive 1 in here, and then you get these 4 equations. Okay, you get these 4 equations, so you get, so the square root of positive 1, of course, is positive 1 and negative 1. The square root of negative 1 is positive I and negative I, and then you get 4 solutions. That's why it's called quadratic equation, I believe, is because there's 4 solutions. It's plus and minus x, and plus and minus y times I. Okay, so you get plus x times the identity. So now I'm putting the identity in here in square brackets like I did earlier. So positive x times the real identity plus y times the imaginary identity. Then you have the negative x times the positive, the real identity, minus y times the imaginary identity, and so on. Okay, and so then, I'll go to my original syntax where I was putting, so this looks actually, this is a nice chunk of code right here. I would call this a nice chunk of code if this was computer code, because nothing is hidden, everything is transparent, and there's no ambiguity. Okay, you've got everything in here. You've got the positive and negative operators. You've got the real and imaginary identities, and you've got the so the real identity is equal to 1, and the imaginary identity, we still don't know what that is. So Euler still doesn't know what that is, and Hamilton still doesn't know what that is. Okay, they just write I, J, and K, but they don't know what it is. Okay, but I know what it is, and you know what it is. If you've been watching my videos, you know what it is, because these are actually complex numbers, and complex numbers are two-dimensional numbers, and the best representation for complex numbers are two-dimensional matrices. Okay, so this is the identity matrix. This would be equal to 1. This is the identity of the 2 by 2 matrix. Okay, this would be the 1 of the complex numbers. This is the negative identity. This would be minus 1 of the complex numbers. This is I. Okay, this matrix here is what I refer to as I, and this matrix here is what I refer to as negative I. Okay, so I'm going to leave it at that. I think hopefully I made my points. I'm pretty sure that Euler didn't know this. So if I were to go back in time and talk to Hamilton, which my friend suggested I do, and of course he's dead, so I have no way of doing that. If I were to go back in time and talk to him about imaginary numbers and complex numbers, I would tell him about this. And of course, you can go back to my other videos. I talk about this extensively. I'm not going to flog a dead horse here about the 2 by 2 matrix, but this is the secret of imaginary numbers. You cannot have an imaginary number. Imaginary numbers are actually simultaneously positive and negative, and that's the difference between real numbers and imaginary numbers. Real numbers are either, so this is the real component of the 2 by 2 complex matrix is either positive or negative, and the imaginary component of the complex 2 by 2 matrix is simultaneously, there should be a plus sign here, I should have put a plus sign here, simultaneously positive and negative. So if I were to go back in time to talk to Hamilton, I would whisper in his ear and I'd say, hey, I have an idea. Let's invent a number that is simultaneously positive and negative. Okay, and let's call that imaginary. So, if I were to go back in time and talk to Hamilton, I might do something like that. Okay, so I'm going to leave it at that, and I hope I made my points clear, and hopefully I can get through to my colleague on this very important point, I believe very important point, about the I equaling square root of negative 1, or using this expression here, I equals j equals k equals square root of negative 1, is maybe foolhardy, because, and this is not, Hamilton did not come up with this idea, so I would have to go and discuss this with Hamilton, because Hamilton came up with this idea. No, Hamilton came up with this idea. I squared equals j squared equals k squared equals ijk equals minus 1. Okay, have a good night.